origin sample size go to infinity. So we can simplify the analysis by doing so, as we know that some terms converges to zero to in the limit. But we may also have a finite sample error. Hopefully, when the sample size is large enough, the error becomes small and we can have a satisfactory approximation to true or exact distribution. The reason that we use asymptotic distributions instead of exact distribution is that the exact finite sample distribution in many cases are too complicated to derive. Even if for Gaussian process, then we use asymptotic distributions alternatives. So method to obtain a limiting distribution, stabilizing transformation, where transform action to make sure the movements do not depend on n. So here, multiply the sample statistic xn by n superscript a, such that the limiting distribution of n superscript a x suffix n has a finite non-zero variance. Then transform action to make sure the mean does not depend on n either. Mean of sample has a limiting variance equal to 0, since variance is sigma squared by n. Multiply by n to the power of 1 by 2, then variance of n to the power of 1 by 2 dot mean equal to sigma square. Check mean of standard variable expectation of n to the power of 1 by 2 dot sample mean were equal to n to the power of 1 by 2 into mu. The stabilizing transformation is n to the power of 1 by 2 sample mean minus mu. So, obtaining an asymptotic distribution from a limiting distribution. Obtain the limiting distribution via stabilizing transformation. Assume the limiting distribution can be used in finite samples. Invert the stabilizing transformation to obtain the asymptotic distribution. As here, take one example n to the power of 1 by 2 in bracket sample mean minus mu by sigma tends to capital 0 comma 1, the standard normal variance. Well, this is in finite samples. Well, n to the power of 1 by 2 sample minus mu by sigma and 0 comma 1. Note we have replaced d for n to the power of 1 by 2 sample mean minus mu and 0 comma sigma square, where sample mean minus mu n 0 comma sigma square by n. Sample mean n mu comma sigma square by n asymptotic distribution of sample mean, where asymptotic distributions, other than a few classical results in mathematical statistics, the exact distribution property of a statistics or other random objects is often hard determining to the last details. A good approximation to the exact distribution is very useful in investigating the properties of various statistical procedures. In statistical applications, many observations say n of them are possible when the number of repeated observations is large. A theory developed for the situation where the number of observations is large from the asymptotic theory. Parameters are the unknown values of an entire population, such as the mean and the standard deviation. Sample can estimate population parameters, but the exact values are usually unknowable. Parameters are also the constant values that appear in probability functions. Parameters are measured characteristics of the population, usually unknown and unknowable at the thing we are most interested in knowing. Statistics are measured characteristics of the sample, which we typically use to estimate population parameters that we cannot measure directly. Statistics are the basic for all of statistical inference, since to infer is to draw conclusions about a population from a sample. Asymptotic is more or less synonym when the sample size is large enough. Strictly speaking, you are considering the limit as the sample size goes to infinity. The way people use is to make approximation based on these limits, where this is ratio estimate. The formula is y bar by x bar. We know this is in sampling. Okay. So where y bar by x bar minus mu by mu equal to y bar mu minus mu x bar by x bar mu. So here, y bar by x bar minus v by mu equal to mu into y bar minus v into x bar minus mu, where n suffix 2 whole power of 1 by 2 y bar by x bar minus mu by mu equal to, this is the simplification. Please go through this. We will get n to the power of 1 by 2 equal to y bar by x bar minus v by mu is asymptotically normal with mean 0. Variance is sigma square by mu square plus n2 by n1 mu square by m mu to the 4 sigma 1 square. Where x and y are independent, sigma 1 square equal to sigma 2 square. Then the asymptotic variance is sigma square by mu square into 1 plus n2 by n1 v square by mu square. So from this, one question we able to ask, write concept of asymptotic distributions, explain asymptotic distributions of ratio estimators. Here you need to write asymptotic distribution definition. This you need to write the first pair of the notes. This you need to write. And next one is ratio estimators. So ratio estimators is what now? So here and this is the ratio estimator. And okay, this is very, very important. And please, whatever the model questions are there, this you please concentrate and read for examinations. So this is the ratio estimators. Got it? Okay. So now, next one is Feller theorem. What does mean Feller's theorem? Feller theorem is not applicable in situation where more than one error mean square occurs. Let mu and v to be two unknown parameters. Let rho equal to mu by v, where it's not v, it's mu, but మీకు ఈజీగా చెప్పాలని చెప్పి వి అని పలుకుతున్నాను. లెట్ పి అండ్ క్యూ బి అన్బయాస్డ్ ఎస్టిమేటర్స్ ఫర్ మ్యూ అండ్ వి. Assume that P and Q are linear in observations that are normally distributed. If cat law equal to P by Q, an estimate of rho, then the upper and lower confidence limits of rho is RL RV equal to R minus GV1 to G22 plus TS by plus or minus TS by Q V11 minus 2 or V12 plus R here V22 minus G into V11 minus V square 12 by V222 whole to the power of 1 by 2 R minus G, where G equal to T square S square V22 by Q square and S square is an error mean square having n degrees of freedom. And the estimates of the variance and the covariance of P and Q are V11 S square, V222 S square, and S square V12 S square V21 respectively, where T equal to Tm1 minus alpha by 2, where P rho Q, then E in bracket P minus rho Q equal to 0, and an estimated variance is given by S square in bracket V11 minus 2 rho V12 plus rho square V22, where M is the degrees of freedom. Thus, in bracket capital P minus Q whole square less than or equal to T square S square, V11 minus 2 rho V12 plus rho square V22 equal to 1 minus alpha. The two roots were obtained by solving the quadratic in row within the probability statement will yield in oral and RU given above. This result will be used in setting confidence limits for the ratio of two means to regression coefficients or a horizontal distance between two regression lines because the latter can be expressed algebraically in terms of the ratio of difference of two means to a regression coefficient. With Q is large in comparison to its standard error, then we can approximately at G equal to 0 and obtain capital R suffix L capital all L Q equal to R plus or minus small ts by Q in the bracket V11 minus 2 capital R V12 plus 2 R square V22 whole power of 1 by 2. T square S square equal to Q square by V22 when G equal to 1. In the product equation, 1 by rho set G equal to 1 and solving the resultant equation, obtain RU equal to infinity where RL equal to R square V22 minus V11 by 2 in bracket R V22 minus V12. Also often we will have equal to 0. That the generic formula is not valid when G exceeds 1.0. Whereas confidence intervals are always wider and those are more conservative than the intervals based on Cressey's prudential distribution. Find the confidence intervals for the natric factor assay given data. Here, one data normal atrial extract with P10 14.2 atrial mean and standardization. So, let us assume that the sodium extraction rates are normally distributed with constant variance. The estimate of the common variance is where x square equal to 7 into 0.745 whole square plus 0.480 whole square by 2. That is 2.2749. And the pool sample and the standard deviation small is equal to 1.658. Here we apply Feller's theorem, set up confidence limits where rho equal to mu by b, capital R is equal to p by q, then the estimates of the variances and the covariances of p and q respectively, where that is v11 s square equal to v22 s square, that value is 2.74119 by 7.39, where 0.393. So here 1 minus alpha equal to 0.90, then small t value is 1.78. G equal to 1.78 whole square 0.393 by 3.345 whole square equal to 0.11, where RU equal to 0.426 plus R minus 1.78 into 1.658 by 3.345 root 7 into 1 plus 0.426 whole square minus 0.111 whole power of 1 by 2 into 1 by 1 minus 0.111. So here R and RU equal to 0.26 plus R minus 0.78 into 1.658, 8.85 into 1.034 by 0.889. Where R and RU equal to 0.426 plus or minus 0.345 by 0.889. Where RLRU is 0.091, 0.867. We assume that the population variances for two extracts are the same. If they are not the same, then one can apply the improvisation for Feller's theorem obtained by Finney. Example, when variance rho equal to, here given the data, variance rho equal to s square 1 v11, q equal to s square 2 v22, and covariance p comma q equal to 0. Then one can easily obtain confident interval rho equal to mu by v, where RLRU equal to R plus or minus capital D by Q in bracket S square V11 plus R square S square V22 minus G S1 square V11 whole to the power of 1 by 2 by 1 minus G, where G equal to D square S square V22 by Q square, where D equal to 1 minus alpha by 2. So explain the concept of Fuller's theorem. Okay. Next one is regression approach to estimate one when u equal to h of x. The equation 1, where f of that is a single variable function of z for all doses the range of interest if Laplace and T are abbreviation for standard tests, then the regression relationships two preparations can be denoted by U equal to H of J and UT equal to H of Z. From equation 3.2, one can obtain the dose ZS and ZR that would induce the average response U. In other words, the doses ZS and ZR are equally effective. There may be some situations where ZS and ZR may not be determinable or may not be determined by uniquely. However, in the case of analytical dilution assays, these uncertainties disappear since the two regression curves must be similar in shape. The relative potency ZS by ZR is a function of U can be plotted in the shape of a curve. Our analytical expression can be obtained. In analytical dilution assays, we make the following assumptions. The response is produced solely by the factor X and nothing else like the impurity. The response to be analyzed is produced solely by the presence of factor X and not by any other substance. The test preparation behaves like a dilution or a concentration of the standard preparation in a completely inert diluent if the two preparations contain the same effective constituent or the same effective constituents in fixed proportions and all other constituents are without effect on you, so that one behaves like a dilution of the other. The potency ratio ZS by ZR, that is R, that is H of Z, H of R for all Z. R is a constant. It is a condition for similar that is satisfied by dilution assays. In summary, the average response introduced by standard preparation as a dose response regression function U H of Z. A test preparation has a dose response regression function U H of or Z, where sigma denotes the potency of the test preparation relative to the standard, namely the number of units of effective constituent of the standard preparation equivalent to 1 unit dose of the test preparation. An estimate capital R of small r is sought to from observations made and dose response tests. If the data arising from a series of tests cannot be described by the same form of regression function for both preparations, then either the assumption of similarity is incorrect or the conditions of testing have been different for the two preparations. It may happen that over a wide range of responses, the two functions are nearly the same, although yet extremes, they may differ significantly. Then the condition of similarity holds reasonably well. In a comprehensive deletion assay, its validity need not hold under condition other than those of. 1 minute, please. Please read this remark. So now space is given here. Write short notes on regression approach to estimate those response and relationships. So next, some exercise problems. Please, I am explaining what is exact distribution in the statistics. Discussion is asymptotic distribution. Asymptotic distribution of ratio estimators. Discussion of Fellow's theorem. Regression approach to estimate those response and relationships. Here, asymptotic distributions, asymptotic ratio estimator, and Feller's theorem. So here, these are the answers, model answers, whatever here given, those answers also given. Please go through these answers. And my dear students, I am again and again repeating whatever the answers in your notes. Please thoroughly read, thoroughly understand, and write in your own words, no problem. Okay? So here given second answer and third answer and the theorem also. Okay, my dear students, all answers pursue, read carefully and answer. What is asymptotic theories in the statistics? Asymptotic distributions, Feller's theorem, statistical inheritance mean. Asymptotic distributions, what is the asymptotic distribution of ratio estimators? State and prove Fellow's theorem, discuss with example. Explain regression approach to estimate dose, response, and relationships. And here, logit someone is logit and probit approaches when dose response curve per standard preparation is unknown. Quantal responses. Methods of estimation of parameters, estimation of extreme quantals. Dose allocation schemes, polychotomous quantal response, estimation of points, and the quantal response function. And here, Luckett and Prohibit approaches when dose response of a standard and unknown quantal response. And here, the main objective of this is define state, logit, and probit approaches. Understand logit and probit approaches when dose response curve for stand operation is known. No quantal response. The logit model uses something is called the cumulative distribution function of the logistic distribution. The PIT model uses something called the cumulative distribution function. The standard normal distributions are defined. F dot both functions will take any number and it fall between 0 and 1. Probit logit functions by taking the logit of the odds. Logit p equal to logit p by 1 minus p. The relationship between logit and probit is almost indistinguishable. Logit equal to log git capital P by 1 minus P, where logit and probit almost indistinguishable. Logit approximately pi by root pi into probit. In general, if response versus dose data are not normally distributed, finally suggest using the logit over the probit transformation. Experimental methods for binary response variables exit for determination of dose associated with the 50% point along the dose response curve or tolerance distribution if the response of the patient can be observed immediately. Logit approaches when dose response curve for standard preparation is unknown. At least two dose levels of the two preparations are required for calculating the respective slopes. If the slopes are not significantly different, the pooled value will be used for the lines. Let dose levels be used where x to log dose for the standard preparation, where x equal to log dose for the lost preparation, where y equal to mean response of n I units receiving I dosage of the standard preparation. where capital Y mean of response and add unit receiving add dose the test preparation, where x bar equal to summation nx by summation n, where y bar equal to summation ny by summation n, where y minus y bar equal to bx minus x bar, where regression coefficient b equal to summation nyx minus x bar plus summation nyx minus x bar by summation nx minus x bar square plus summation nx minus x bar square, where cat lam equal to this, and these are the formulas where s square equal to sum of the square deviation from group means by summation n1 plus n2 minus 2. Consider the following artificial data pertaining to weight pay gain in pounds by we get in a fixed duration of time when standard and last preparation of a certain diet and administered to them. So here standard preparation, test preparation, unit 1, unit 2, unit 1, unit 2. It's mean and y bar mean, and we can calculate s square, that is the pooled variance, and regression coefficient, that is formula r sigma by x by sigma bar. So here x and y values is given. From this we can calculate r values. Please go through this. Please see this. The table, please see standard preparation, test preparation, the values given unit 1, unit 2, unit 1, unit 2. Next, write short notes on logit and probit approaches. Next, probit approaches when dose response curve for standard preparation is unknown. An estimate of potency based upon individual observations that vary widely is of little use unless supported by some indication of its limits of error. Standard errors of the mean tolerance can be calculated by familiar process, and from these must be derived a measure of precision. Consider first the two tinctures alone, writing Z as a typical dose. Sum of squares of deviations are used to estimate the variance of Z bar 1, Z bar 2, the two mean doses for instruction 1, S Z minus Z bar 1. Instruction 2, S Z minus Z bar 2. Both sum of squares between minus 1 degrees of freedom. Hence, practice of pooling the sum of squares so as to obtain a single estimate of variance per cat seems reasonable. The logic flaw is discussed involving writing s square equal to sum of two means dosed by size 1 plus size 2 minus 2. Two variance of Z1, variance of Z2 were equal to S square by size. The square root of this is the standard error, x bar 1, x bar 2. The equation can be written as capital R equal to Z bar 1 by Z bar 2. A standard error for capital R can be calculated with the aid of a commonly used approximation formula. So here, some of the problems with application. So these are S squares. Yes. So here, these are the problems where we calculated covariance variance of R. Now, the question is, space is given below, writing your answer Um, so the question is write briefly notes on probit approaches, Windows response curve for standard preparation unknowns. So the next one is quantal responses. The quantal response in a biological assay is usually so quantal responses. The quantal response in a biological assay is usually based on two possible outcomes. A common example of the two possible outcomes is death or survival. However, there are several assays, such as that of some insecticide based on the mortality of the housefly. There are three possible outcomes, namely active, moribund, and dead. There is a defined order of these outcomes. Active precedes or moribund, which in turn precedes dead. It may be more efficient categories. An approach to the problem based on the method of maximum likelihood has been given by Edson Silve in 1957 and Ashford 1959. Goulrod 1960 provide a general method of analyzing the data when one uses the normates, logates, or other obtained by minimizing the appropriate C2 expressions and have the sympathetic properties of consistency and efficiency. The latter set of authors provide a numerical examples involving the housefly insects. And here, maximal information from bioassays in 1966 draws the following conclusions based on empirical studies. It is advisable to utilize graded response such as body weight and organ weight, percentage of blood sugar, or any measure that can be quantitatively expressed rather than planning or essay 71 quantal responses, categorizing responses into grades 1, 2, 3, and 4 will usually be superior to a purely quantal measurement. The weights used in probit analysis of quantal responses illustrate that a graded response provides, on the average, about the twice the information of a quantal response. Also, graded response is more useful because the latter can be measured over a wider range than quantal responses without running into extremes. Quantal responses based on groups of animals are preferable to a series of single observation at several dose levels. Also, observations derived serially from the same animal may be 4 to 6 times as precise as observations made simultaneously upon different animals, sometimes of genetically homogeneous material. And See the table. I'm going to explain this maximal information from bioassays MNs 196. This also I explained where this is in the present study, the percentage of subjects responding is plotted against log 10 dose. A sigmoid curve will generally be the result. A transformation is needed in order to obtain a straight line. If k dose levels are considered and the proportion of units responding at level I as is Pi, where a plot of suitable transformation T of P of the P against log 10 dose will be an approximate straight line. The line can be fitted by usual least squares method. However, with the quantile data, the points do not all have equal weights, even though the number of experimental units in each group is the same. This is the main difference between the case of quantile response and that of a quantitative response. Now, the computational advantages of the logarithmic transformation are readily seen by application to the data. The logarithm of the tolerance in 4.2.1 are shown below. Here, Strophant plus 1, Strophant less 2, out over min. So this is the data that mean and standard error and covariance. Please see this table, note down and analyze this. Okay. Here we can calculate F ratio. You know that S1 square by S2 square. And here we have calculated these two SHX. You know what, so this one first column and second column, those value 0.4621, 0.0352. So here the population variance of S square by n is this, and this you substitute here, you will get the value S square pooled variance is 0.00489, where 20 degrees of freedom. The symbol caplem as an observation for large R will be used for the estimate of log potency from equation log Z plus log rho equal to log ZB. Its value for tincture from related to tincture 2 is M equal to x2 bar minus x bar 1. Moreover, variance is 0.0493 whole square, where ml equal to 1.972, EMU equal to 0.17 lakhs. The anti-algorithm of Kaplan and its limits give the relative potency and its limits. These are 1.1 n mu per mu L with limits 0.94 mu per mu1 and 1.1 mu1 per mu1, very similar to the results in precision of estimation. Similarly, for the potency of the wind preparation related to tincture 2. So here the values are this. The compare. So what does mean quantum response in the biological assay? So the questions, what are the logit and the probit approaches What are the Luckett approaches when the dose response curve for standard preparation is unknown? What is the Probit approach when dose response curve for standard preparation is unknown? Discuss quantum response in biological assay. State Logit and Habit approaches. Probit approaches when dose response curve for standard preparation is unknown. So now these are the model answers are given, and please go through these all answers. Each and everything you read, you will able to answer in examinations. The next one is methods of estimation of parameters, estimation of extreme quantiles. Estimation of extreme quantiles. This we discuss tomorrow. If you have any queries, I am sharing once again the notes. Please go through that and ask the questions to me. So, okay, this is the topic we will explain tomorrow. Tomorrow. Okay. So tomorrow is the date is 8 and 2 and 2 4. Okay. So I'm sharing once again, dear students, please go to the topic and ask me any doubts. I will. Okay. Thank you, dear all students. So thank you, dear all students. And tomorrow I will start Unit 5. Unit 5. So I'm sharing once again the notes today. So this is the data. Once again, you note down what is the total, what is the mean, check out and check the mean is correct or not. Congratulations. Okay, please go through the notes. If you have any queries, till unit 2 4, 1 to 4, and please ask me, I'll explain. I'm requesting you, students, please go through the notes only, and please go through the model answers questions and try to practice, then you will pass. Please, I hope you will understand that. Okay? Thank you for giving this opportunity, BRUU team, and especially Vijay Kumar sir. And thank you, the students.